Okay, so let's go through an example on how to actually write a program, and we'll do this for an actual a view factor that exists in a library, so we can just compare the values. Okay, so here's a case where we have two surfaces. We have a surface in the XY plane, and then we have a surface in the XZ plane, and they're separated by some space. So obviously we can calculate this with the library. You can just go to ease and find this one. But we'll double check it with the ray tracing just to prove that we can do it. Okay, so the first thing we want to do is we're going from surface 1 here to surface 2. So we want F1 to 2. So our emitting surface is going to be surface 1. We need to first decide, let's start sampling random positions on surface 1 for our rays, and then send them out. So let's pick a random position. Again, we've got a random position here. We need, here's our coordinate system. We're gonna need to pick angles. So again, let's pick an angle. Let's draw it this way for simplicity. So our ray is gonna be sent off this way, and that corresponded to a particular theta and a particular phi that we had sampled. One thing that's actually a little subtle here, and we need to step back before we continue on, is when I'm sampling, I need to make sure that there's an equal probability that anywhere in the hemisphere around the emitting ray has an equal probability of receiving a ray. Okay, and if we just randomly sampled theta and phi by taking their extent, say 0 to 90 degrees for theta, or 360 degrees for phi, and randomly sampling from that range, we wouldn't be doing that. And to think about why, let's look at this example. So let's say I have an emitting surface up here. That's a circle. All right, my circle is an emitting surface. What if I took my coordinate to be, 0 to r? So I'm going to pick a position on here from 0 to r. And I'm going to pick an angle theta. So if I were to randomly sample from 0 to r, I might have an equal probability of being anywhere on that radius. And then when you are anywhere on that radius, then you have to look all the way around the circumference, right? So the idea here is if I were to do that, randomly sample from 0 to r, I'd be favoring what's happening in the middle much more, right? Because there's less area associated with that ring in the middle than there is the rings at the outside. So in order to deal with that, we actually have to correct when we're doing sampling in coordinates where this type of thing is happening. You have to correct based on the actual area that's corresponding to that random sample. Okay, so what we're saying here is when I sample, let's back to our problem here. Let's start with phi, right? So I'm going to sample phi. Phi can be sampled in the range from 0 to 2 pi, right? Or 0 to 360 degrees. And that's going to be just some that we call P of phi, some probability distribution. P of phi is a uniform distribution, okay? So I can take a uniform distribution, I can sample in phi, and I'm not going to be favoring any angle or anything like that. Theta, though, is a problem, right? Because if I look at that dome around the normal vector, I'm going to be really favoring what's close to what's close to that normal vector because there's less area associated with that. So you have to actually correct it, and the correction for this is theta. Our random sampled theta is going to be the inverse sign or arc sign of the square root of p theta. All right, so p theta is again a uniform distribution on theta. So I can do a random sample of 0 to 1, plug that sampled value into square root of arc sign of that argument, and then I get back my actual sort of corrected distribution sample for theta. Okay, so that's the way to do that on polar coordinates. You can, it's not obvious where that comes from, but you could do it if you just sat down and look and work through the area part of the equation. Okay, so all right, so we have now our theta and we have our phi and we have our ray direction. So then what's the next thing? So we need to come up with a normal vector. So we're going to call this normal vector or this direction vector R. Okay, so R is going to be this, let's break this out into vector components. So let me draw this a little bit bigger over here. So we have our coordinate, this is our emitted ray, we have our coordinate system. We have y, z, and x. And we have our emitted ray. Let's draw an emitted ray like this. So if I broke this into components, it would be, let's see, this. So that's the projection. This would be the projection of that ray into the coordinate system. So we need to think about the length of each of the components of this vector. Right? So again, we have our angle here. This is theta. This is phi down here. So this, let's see, how do I draw this? So this segment here, right? This the vertical segment is going to be what? It's going to be a cosine of theta, right? Let's see, the x component here, right, this x component is going to be sine of theta times cosine of phi. That's our x component. And then the y component here is going to be sine of phi times sine of theta. Convince yourself that that's right, just based on geometry. But so now we have right, the I, j, and k components of our vector. And we can just write this vector out in terms of that. So our vector is going to be what, cosine. It's going to be cosine of phi sine of theta times I. So I is going to be our right, x direction vector or x direction unit. So we'll put a little underline under that. Plus the j part, which is going to be sine of phi sine of theta j plus now cosine of theta k. Right, so this is a unit vector, magnitude 1, that is describing the direction of our ray that's leaving the surface. Okay, so then right, the next thing is we've got our direction, we've got our location. Now we need to decide, has this thing hit the surface? So for this problem, we've constructed a problem that's pretty convenient, right? We can solve for, if we just sort of trace along this ray, we can solve for where this ray is going to intersect with the xz plane, which is at y equals 0. So we could say, let's solve this where y is equal to 0, and then get the length of the ray, and then we can see what our other coordinates are. Okay, so we'll do that. Let's see here. Let's go to the next page. So here's our target. This is the target we're trying to hit. So let's write out, what is this? So this is going to be the location of where it's hitting. So this, we'll call this capital R. And so this is going to be the location of where the ray is hitting in this plane, in this xz plane. So R is what? It's going to be the starting point, x0 in I, plus y0 in j, plus z0 in k, plus the unit vector, R, times some length of the vector, right? We don't know what that length is yet. But it's going to be the distance that the photon would have to travel from its emitted position to where it hits on that plane. Okay, so let's see. Let's just write this out all the way so we know what these components are. So R underline is going to be, this x0 part is x0 plus L times cosine of phi sine of theta I, plus the j part is y0 plus L sine of phi and sine of theta in j, and then plus the k part, which is z0 plus L cosine of theta in k. Right, so that's where we're hitting. We do know, like I said, that this has to be at y equals 0. So we could force this y part of the equation, just consider the y part of the vector and then force that to be equal to 0 and solve that then for L. So we could do that here. Let's say y0 plus L sine of phi sine of theta is equal to 0. That's our y coordinate. It has to be equal to 0. Again, now for this is our problem here. If you have a different problem where that's not the case, you have to put some thought into where is that happening, right? It's not going to be at 0, it's somewhere else. But this is just our example for now. Okay, so then we solve for L. L gets us equals minus y0 over sine phi sine of theta. Okay, so then we can use that. We now have L, and then we can plug in L and we can get the other components, right, the other intersections. So let's see, that gives us X. Our X intersection is going to be X0 plus L cosine of phi sine of theta. Z intersection is equal to Z0 plus L cosine of theta. Okay, so we have yi, or y intersection 0. We have now xi and vi. We can solve for those. And so we just have determined the location. Now we have to apply some tests to see, is this in our rectangle? Again, this is a really simple example. Right? This is, you have a rectangle, we can say, is my ray hit between what, B1 and B1 plus B2 in the Z direction? And is it between 0 and C in the X direction? And so we would say, let's just go through and say the ray hits 2 if all these things are true. So it's going to be 0 is less than xi, which is less than c, right? You might even do it. So let's think about this a little. I'm using less than, but you could use less than or equal to. One thing to think about here is when you're writing a program, if you write less than, the program does one test, right? It says, is this number less than this number? If you do less than or equal to, it's going to do 2 tests. So if you're repeating this calculation, 10 million times, it might actually be a significant thing to write it as less than versus less than or equal to. So actually what you might want to do is think about the computational expense of each of these little things as you're going through. So we write it as less than just because it saves us a little bit of computation. And it's only captured in the case where you're exactly hitting the edge, and it's really unlikely for that to happen. Okay, so this is true. This is true. It also hits when B1 is less than Z, which is less than B1 plus B2. And the third requirement is that I'm going through and solving this. Let's look back up here for a second. So I drew my vector off pointing away from the surface. This vector, if I solve for where that vector hits that surface in the XZ plane, it's going to be a negative length, right? My ray that would be missing the surface could solve for an intersection, but it's going to be at a negative length. So I want to make sure that I go through and remove any rays that solve with a negative length, because those actually are going off into space some other direction. So my third criteria for this problem is L has to be greater than or equal to 0. You could theoretically have a problem where the ray is emitted right at the edge. But so again, you could just make this greater than 0 if you wanted to save a little computation. All right, so these 3 criteria, all we need then to evaluate whether or not this is a ray hit. And then we just go through and we tally everything up, repeat the process, and we have a program.